Welcome to this explainer. Today we are uncovering the hidden molecular mechanics going on right inside your own kitchen and, honestly, all around your house. We're going to look closely at the fascinating ways materials transform from, the simple act of melting some Blue Band margarine in a hot pan, all the way to the intense heat of burning charcoal in a traditional sajiri. Because, as it turns out, there are incredibly strict rules governing exactly how everything in our universe actually changes.
We see things transform around us literally all the time, right? But consider this for a second. Why is it that some things, like melting that margarine, or, say, freezing water into ice cubes, can easily just turn right back to their original state, while an egg, well, once you drop it into boiling water, it's changed forever? Seriously, why can you never unboil an egg?
Okay, so let's dive into this with the absolute golden rule of chemistry. To figure out any change you see happening out there in the world, you always have to stop and ask yourself one totally crucial question. Did we make something brand new? That's it. The answer to this single question basically acts like a massive fork in the road, splitting all chemical and physical reactions into two highly distinct paths.
So if your answer to that golden question is no and nothing brand new is actually created, we call that a temporary or physical change. This basically means reality can be reversed. Now, if we zoom into a molecular level, what's happening here is that the actual chemical bonds holding the material together, they remain perfectly intact. The only things changing are the distance and the energy between those molecules. So think about boiling water. It might turn into invisible vapor, absorbing heat and spreading way out, but deep down, its core identity hasn't changed one bit. It is still just H2O.
But if the chemical structure fundamentally alters, creating something completely brand new, well, that is a permanent change, also known as a chemical change. And guys, this is the path of no return. The reason it's so permanent is that the actual atomic bonds have literally been broken apart and reconfigured into entirely new molecular structures. Once you've created this brand new substance, it becomes incredibly difficult and mostly impossible to undo it without kicking off another massive chemical reaction. You have irreversibly changed the matter. There's really no going back.
And understanding that dividing line between these two paths, it gives you the ultimate cheat sheet for decoding the world around you. With temporary changes, there are no new substances, and they're highly reversible. Think about things like melting ghee, dissolving sugar into your tea, or just hanging your clothes up to dry in the sun. Permanent changes, on the other hand, mean brand new substances are formed, like a rotting tomato, cooking matoke, or a resting bicycle chain left in the rain. And one of the most fascinating scientific little quirks here is how mass behaves. In a temporary change, the mass stays exactly the same. But in a permanent change, the measurable mass can actually shift if the new substance involves gases that happen to escape into the surrounding air.
All right, Section 1, temporary changes, and how we're reversing reality.
Let's start with our first deep dive into these temporary changes, where things might look completely different to the naked eye, but are actually just doing a physical shift. A perfect example of this is dissolving salt. When you stir salt into a glass of water, it seems to just vanish entirely, right? Like magic? A lot of people mistakenly assume this means the solid is gone forever and a permanent change happened. But we aren't dealing with a disappearing act here. We are dealing with electrostatic dispersion. The crystalline salt matrix is simply being pulled apart by the water molecules into individual sodium and chloride ions. Those ions just disperse evenly throughout the water. They haven't fundamentally changed their chemical identity at all. They've simply separated.
And we can easily prove it's just an illusion by reversing the whole process. You dissolve the salt, sure, but then you apply heat and boil away all the water. Once the water vaporizes, just look at what's left behind in the pot. You get your salt back, exactly as it was. This proves beyond a shadow of a doubt that no brand new substance was ever formed. Those little ions simply rebonded right back into a solid crystal matrix the second the water left. Now, consider the action of breaking a wooden stick. It might feel like a permanent change because, obviously, you can't just snap your fingers or use glue to seamlessly put the cellular structure back together exactly the way it was. But remember our golden rule. In reality, it is still 100% wood. The shape changed, sure, but the chemical substance didn't. No new atomic bonds were formed, no ash or smoke was created. Therefore, scientifically speaking, it is just a temporary physical change.
Moving on to Section 2, permanent changes, no going back.
This is the territory of irreversible transformations, where chemical structures are altered forever. So how do you know for sure that a permanent change is actually taking place without, lugging around a high-powered microscope?
Well, your own senses are actually your best scientific instruments. You know what permanent change has happened when you detect dramatic chemical shifts, entirely different colors, completely new smells, or drastic changes in how a material behaves. These are prime indicators. The sudden formation of ash, smoke, or flaky rust? That means you've just witnessed a permanent chemical change.
A really classic example of this is rust. When a strong iron nail, a bike chain, or a heavy iron roof is left out in the rain for a few weeks, a chemical reaction kicks off. We call this oxidation. The iron atoms are literally binding with oxygen atoms from the air, which is catalyzed by the water, to form a completely new molecular lattice. The final result is iron oxide, which we all know as rust. The original durable iron is gone forever, completely replaced by this much weaker, flaky brown material. It is a total, fundamental rewiring of the atoms.
And hey, that brings us right back to our egg. Think about boiling an egg, or even mixing maize flour in hot water to cook some posho. The heat here serves as a catalyst for a chemical reaction. In the case of the egg, the heat is actually denaturing the proteins. It basically causes their tightly coiled chemical bonds to unspool and then violently tangle together irreversibly. That process transforms a runny, clear liquid into a firm, bouncy white solid. You've created a completely new molecular structure that you can literally never uncook. Which leads us to Section 3, the two faces of heat. Now here is a truly fascinating twist. Heat isn't just a trigger for permanent changes like cooking, it can actually act as an agent for both temporary and permanent changes at the exact same time. Just take a really close look the next time you light a candle. The heat from the flame melts the solid white wax into a little liquid pool right beneath it, right? If you blow the candle out, that liquid wax quickly freezes back into a solid. That's a temporary physical change. But look at the flame itself. The burning wick and the wax vapor that actually catches fire to produce black soot and smoke, now that is a permanent chemical change. You are witnessing two totally different scientific processes happening simultaneously, all from one single source of heat.
Heat can also cause a beautiful, somewhat rare type of temporary change called sublimation. Sublimation happens when a solid changes directly into a gas when heated, completely skipping the liquid phase altogether. It doesn't melt at all. Instead, its molecular bonds absorb so much energy so quickly that it just vaporizes instantly into the atmosphere.
For example, if you gently heat black iodine crystals in a glass tube, they do not melt into a liquid puddle. Instead, they sublimate directly into this absolutely stunning, bright purple gas. But remember, this is a temporary change, because as soon as that hot purple gas floats up and hits a cold surface near the top of the tube, it loses that energy and instantly turns right back into solid black iodine crystals. It completely reverses reality once again. No new substance was ever made. It just dramatically changed its physical state.
Bringing us to Section 4, why knowing the difference actually matters.
So, why does understanding this difference matter to any of us outside of a sterile science classroom? Well, it matters because recognizing these changes literally gives us the agency to control our environment. When you freeze your food, you are intentionally using a temporary physical change to halt a permanent chemical one, which is rotting. An engineer building a bridge uses special paints to block oxidation and prevent the iron from permanently rusting away in the rain. And understanding permanent chemical combustion helps us know exactly how to safely use, control, and ventilate fuels, like burning charcoal, right inside our own homes.
By thinking like a chemist, you hold a whole lot of power. When you see something transforming, if you just stop for a second and ask yourself if you made something brand new, you can deeply understand and even manipulate the physical world around you. You basically stop seeing magic and you start seeing the mechanics of reality.
I'm going to leave you with a final little puzzle to test your new perspective. When you crack open a fresh, fizzy bottle of soda, bubbles of carbon dioxide gas immediately rush up and escape into the air. Think about it for a second. Did you just create a new substance, causing a permanent change? Or was that gas just dispersing, making it a temporary one? Use your golden rule. Thanks for joining me on this explainer, and definitely keep questioning the world around you.